function on the reals, right, then there exists unique extension of f to, what's my notation? I guess I call it f tilde. And the formula for the extension is shockingly just this: sum n equals 0 to infinity. Use the same coefficients. Z power n. I don't need a star this time, because notice that if it's an entire function on the reals, what can you say about the coefficients here? These are real numbers, right?
Yes.
So I don't force myself to write the star when I'm just writing a real multiple. The proof is pretty straightforward.
Yeah.
And now, as I talk to you about this now, there's a different question, right? Which is, if you have a function, right, which is entire on the algebra, does it necessarily restrict to a function which is entire on the reals? That's the other direction. You see, this is like if entire on the reals, then extends to entire on the algebra. What if you had a function which was entire on the algebra? Does that restrict to, let me try to figure this out.
I know what you're saying, but I'm just trying to think about. So we're talking about like straight up like R into an algebra.
So I'll say f tilde
Mm-hmm.
from the algebra to the algebra, right?
Yeah.
Such that entire means that f tilde of z is equal to the sum n equals 0 to infinity of cn. I'm using an, right? So an star z minus, well, star z to the n. All right, it's entire. I can make it 0. So we know that the reals are a subset of the algebra, you know.
If the reals are a subset, then I would say yes. If it's entire on the algebra, it's entire on the reals.
Right, so let's see here. So let's see here. If we set z equal to t, or maybe x, let's use x. Z equal to x in the reals, right? So like, I'm saying evaluate f tilde and define, let's say f of x equal to f tilde.
Oh, wait, but what if you have like a... Because the reals are plainly complex, but it's just because you have it over the complex, it's if it's entire over the complex doesn't mean you get a defined point like an I and stuff.
Yeah, I think we're, well, I mean, let me just complete this thought here. I'm just kind of playing it. I don't know for sure what the answers to this are. So f of, just plug in x.
Yeah.
And like I'm defining f of x by this, right? But that is the sum n equals 0 to infinity of like an star x to the n, right?
Yeah.
Of course, the star is not needed here because x is real. So I can rewrite this as f of x equals to the sum n equals 0 to infinity of an x to the n. But here an are in the algebra. So an and r are not given, right? Which is to say, more to the point, f of x element of r not given, right?
Mhm.
So my naive idea is just restrict the input isn't going to work. That's not enough, right? What else are we going to have to do? We're going to have to.
Well, I'm just saying that, like, you know, since f tilde of z is a function on the algebra,
Mhm.
you can expand it that using a power series, that you can plug in I, unless you restrict I.
Well, if there was an I in the algebra,
Yeah.
I mean, there's not always a imaginary unit in every algebra, right?
Yeah, I know, but like, I'm just using that one example because, like,
Oh, well, yeah.
if you prove it for one, that means it's not always the case that means you can't say.
But if I could,
Are you saying we find out? Or,
I'm trying to construct a real series,
mm-hmm.
which is also entire. So I'm trying to say, to every entire function on the algebra, there exists a corresponding entire function on the reals. But I'm really trying to, but I'm doing something a little bit stronger than that even. I'm saying that if you restrict the entire function on the algebra to the reals, maybe.
I'm thinking about it in like a complex case, not like an abstract though. I feel like that's the easier job to, like, yeah, you could just restrict all the points on it. Because the only thing that's not real, like, because you could restrict to real values only in a complex plane.
The real values of the function, right? That's the thing I haven't done yet. Is like, so what, we could take the real part of it though, right?
Yeah. Just take the a part, because there's a real line, and take the a part.
Right. So like,
say that we throw out the I and negative I.
yeah, something like that. So like, for an arbitrary algebra, this is like something like what this is f0 of x plus f1 of x times v to f2 call f1. There's component functions, right?
Yep.
And those are well defined because we can expand this into basis, and then we can pick off the coefficient of each basis element and define the coefficient, the component functions of that. And I suspect that maybe we can argue, maybe, here's my suspicion, claim that f1 of x, right, which is going to be the sum, yes, sum n equals 0 to infinity of, I don't have a notation for this, but let's say a n comma 1, x to the n is entire, where, you know, an is equal to an comma 1 plus an comma 2 v2 plus da 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 plus a, bad choice of notation. Oh, I told you we were going to not do this. My bad. So the dimension of the algebra, I had best not use n, little n for that, because we're using little n in a different way here, right? I should have used like big N or something for the dimension of the algebra.
Mm-hmm.
So if I do that, I should put a sub little n, big N, the n. So my point is that these are the real components of the coefficients.
Yes.
So I feel like it's possible that you could find a entire function on the algebra, right?
Mm-hmm.
Where you built the coefficients such that they have no real part. So that when you go through this construction, f1 of x is just identically 0.
So
I mean,
are you trying to get a constant function in the real zone? Like you're trying to get some constant function?
that's not, I mean, I would, that's not bad. It's just like, I can see right now that I don't necessarily get a non-trivial entire real function if I'm so unfortunate to have chosen my original algebra constants to be like, not have real pieces, you know? So, but I do think you can argue that that's entire because, yeah. Huh. I actually kind of have a suspicion, Audric, and I could be wrong about this, but my suspicion is that if we take an entire entire algebra function, and we like restrict to any line through the origin in the algebra, it may be that we can argue that the corresponding real part of the restricted function gives us an entire real function.
And that's all you need, not the whole thing.
Yeah, well, I'm just kind of curious about this. Okay, so what we're about to do is I'm about to explain to you how we can define exponential, sine, cosine, cosh, sinh, all of our favorite functions on the algebra. And the way that's done is just to say, okay, well, sine, cosine, exponential, cosh, sinh, these are all entire functions over the reals. They have power series, which if you apply the ratio test to, you get 0.
Yep.
Which means that they have a radius of convergence of infinity. Like the power series for sine, cosine, exponential, cosh, sinh, they just go on and on. And so correspondingly, corresponding algebra functions are likewise entire, and they're actually defined by series with the same coefficients. So like to define exponential, sine, cosine, cosh, sinh, all your favorite elementary functions, we can give power series definitions over the algebra. And those functions will naturally restrict to the corresponding real functions in the center of the algebra. But what I'm just kind of wondering about is what other functions are out there for the algebra? Like, are there sort of, in some sense, non-standard versions, if you will, of sine, cosine, these other functions that are built off not extending the real function on the real line in the algebra, but instead of basically based on extending the entire function that's somehow like weirdly embedded in the algebra. Those would give me other functions I haven't thought as much about.
My question is that if we can build an entire function on the algebra using the reals, we should be able to go the other way. Like
Yeah, I think so. I just haven't thought much about that other direction. Is my point. Like,
yeah.
So I don't know if you've ever seen this before, but we can actually define all of your favorite functions from calculus, like many of them, using power series. So, but it's not just that. Like all of the properties that you know about sine and cosine and the rest, they can all be derived from power series arguments. So like definition, e to the x, sum, n equals 0 to infinity, 1 over n factorial, x to the n, right? Cosh x, sum, let's say j equals 0 to infinity, 1 over 2j factorial, x to the 2j, sinh x, sum, let's say j equals 0 to infinity, 1 over 2j plus 1 factorial, x to the 2j plus 1. And then of course your cosine of x, sum j equals 0 to infinity, minus 1 to the j over 2j factorial, x to the 2j, sine of x, sum j equals 0 to infinity, minus 1 to the j over 2j plus 1, factorial x to the 2j plus 1. There's the usual suspects right there. And you can prove that these are entire on the reals, because if you look at their coefficients, like I said, if you apply the ratio test, you get 0. Consequently, the lim sup of the coefficients here is 0 for all of these. Alpha is 0, which goes to show you that these are entire. And so to create the corresponding algebra functions, right? It's really simple. All you do is replace x, the real variable, with z, the algebra variable. I mean, that's it. So I'll do it. But the cooler thing still, right, is that all of the properties that you know and love for these functions can be derived from the theory of series, theory of power series. So like, just to give you, I mean, there are lots of examples, but check this one out. So you can easily see from the term-by-term differentiation that the derivative of cosine is minus sine z, and the derivative of sine z is cosine z. See, because if you differentiate sine z term by term,
Yeah.
this brings down to 2j plus 1. You get 2j plus 1 over 2j plus 1 factorial, which is 2j factorial, because just the 2j plus 1 cancels in the factorial. And,
Oh, yeah, that gives you cosine, yeah.
right, and then so like, except at the lowest order where, well anyway, I think that ends up, yeah, that gets you, I'm trying to remember. Yeah, that's it. And then in contrast, when you differentiate the cosine, you get 2j over that, but the thing is, it leaves you with 2j plus 1, and if I was more careful, there's a reason the minus comes out. I mean, we could work it out if you want.
Yeah, sure.
Right.
But I have an idea of how it's going to work out.
Let's see here. So let's try that out. d dz. I'll just sum j equals 0 to infinity of minus 1 to the j over 2j factorial z to the 2j, right? Right. So that's equal to the sum. The same thing gets me into trouble in differential equations and also calculus 2. So sometimes we'll rewrite the summation starting from 0 to 1 when we apply this rule, but you got to be careful. That only is legit when the powers are ascending by 1 each index of summation. When they're ascending by 2, you don't get to, it's still j equals 0. I mean, you can always leave the summation alone and you just have some zeros early on if you look at the term-by-term theorem. So we could write the term-by-term calculus theorem not adjusting the sum. Anyway, we've got 2j over 2j factorial, right? Z to the 2j minus 1. That power, differentiate that. Differentiate this with respect to z, I get 2j times z to the 2j minus 1. Now, of course, 2j over 2j plus 1 2j over 2j factorial is 1 over 2j minus 1 factorial, right? Now this is where it gets subtle. Notice that I've written this 2j plus 1.
Wait, why would it be 2j minus 1?
Because, well, that's what the math did to us. Now what we can do is change the summation, all right? So, let's see here. Let's see, if I say 2,
Oh, I got it, yeah. Okay.
goodness gracious, I'm trying to have trouble here. 2k, if I say, here's what I want 2k plus 1. What I have is 2j minus 1. How do I convert this? What does that say? It says 2k is 2j minus 2, right? It says my k is j minus 1. Or j is k plus 1, right?
Catching up, sorry.
You're fine.
2j minus 1. We got that, and then that goes to that. Okay. Z 2j minus 1. And what are you doing on the left here with the purple?
Well,
I'm with you here.
yeah. Well, I'm trying to make it look like my series for sine.
Can you rewrite? Like, because it's essentially like the same thing though. Should be in the minus 1.
I'm not sure about what I'm writing at the moment.
That's not gonna work.
Yeah, there's something, I don't know what I'm doing wrong, Audric. Like, there's something that's not quite right. I mean, it's completely stupid if you just write it out. You know, this is 1 minus z squared.
Oh, we're missing a minus somewhere.
Yes, I know. I'm not sure how I'm doing it. That's that series, right?
Yeah.
This one.
If we can find
1 over, 3 factorial z cubed. Right, so when you differentiate this thing, when you differentiate this thing, term by term, you get 0 minus 2z, plus 1 over 3 factorial z cubed. So why am I not seeing that?
GTC.
Oh. Oh. Because I'm an idiot. And it's really, oh goodness, yeah. Woo, man. See it now. This is quite dastardly. This is only for j not equal to 0.
Yeah.
See, when j equals to 0, this is a -1 factorial, which is not a thing.
Yeah.
This algebra only holds for beyond 0. All right? Now at 0, you've got 2j, which is just 0. So you've got 0 over 1. That's just 0.
Mm-hmm.
So it starts at 1. Only at 1 is this simplification valid, and the thing that I'm dropping, j equals 0, is just 0. That's it. Now, once you've done that, then we can make the substitution I was just suggesting. J equal to k -1, or k...
No, you put, it was a 2j minus 1 plus.
I think j was k plus 1?
Yeah.
Yeah, so if j is k plus 1, when j is equal to 1, k is equal to 0, right? I'm sorry. I think I need to drink more coffee. All right, k equals 0 to infinity. And so that's -1 to the k plus 1. And then that will be 2k plus 1 factorial z to the 2k plus 1, right? When we make this substitution to go from here to here.
You have to drop a 1, don't you? If j is equal to 2k, to k plus, oh no, you don't. Gotcha, I'm with you.
And then the thing is, we just go and then that is sine. That's sine. So what you got here is minus sine z. Of course, and then I was right in the world. Derivative of cosine is minus sine.
Why did you take out, how did you take out the k plus 1 on the top?
Well, -1 to the k plus 1, which what we had
Mhm.
originally. That's -1 to the k, times -1 to the 1.
Oh.
It's just minus. Yeah. Alright, so if I wasn't such a doofus, we could have had this 10 minutes ago. The point is, you can differentiate term by term and derive derivative of cosine is minus sine and derivative of sine is cosine. Alright? And then you can also prove, remember the theorem in calculus 1, if the derivative is identically 0 on some connected set,
Mm-hmm.
then the function's constant.
Yes.
Still true here. So, can I erase or you still?
No, you're good.
So, with that little theorem in mind, you let f of z equal to cosine squared z plus sine squared z, right? And so df dz is,
0.
is 0, right? Because that's 2 cosine sine, and that's 2 sine cosine, but one's got a plus and one's got a minus because of the chain rule. And so that implies that f of z is equal to f of 0 for all z in the algebra. But what is f of 0? It's cosine squared of 0 plus sine squared of 0, right? What's cosine of 0? Like cosine of 0 is 1. You can see that from the power series. Sine of 0, 0. So this is 1. So you can prove cosine squared plus sine squared is 1. completely from just calculus. There's no geometry here at all. It's just straight analysis, power series, calculus. And you know what? If you just add an h, what happens? Derivative of cosh is sinh, no minus. Derivative of sinh is cosh, no minus. So you need a minus down here. Because then you get 2 cosh sinh minus 2 sinh cosh, 0 for all z. So f of z is equal to f of 0, but cosh of 0 is 0. Cosh of 0 is 1, and sinh of 0 is 0. So this gives you cosh squared minus sinh squared is 1 for all z in the algebra. What I think is perhaps even more impressive, though, is that you can derive other things using calculus on the algebra. Like, it's much more than just this. You can prove, for example, using completely power series arguments, that e to the z times e to the w is e to the z plus w. You can prove that using series. You can prove that cosine of z plus w is cos z cos w minus sine z sine w. That can also be proved using just calculus on the series.
Yeah, I see the EZ and e to the w, like I did it pretty quick in my head there. Like just using that.
Oh yeah, just you multiply those
Yeah,
out,
no,
use
yeah.
binomial theorem and such.
But the trig identity now.
Yeah, the trig identity is not obvious.
Yeah.
And so like let's look in the paper. All of these are this is the lion's share of like a lot of this paper is that. The thing you did in your head with the e to the z times e to the w, what that actually requires is corollary 5.25, which says that the product of two entire functions is itself an entire function, where you construct the coefficients for the product function by appropriate series of products of the functions being multiplied. So what that really says is that you multiply power series like normal, collecting terms of each order. Anyway, let me get on here. So section 6, 28, there's the exponential. Are you there?
Yeah. Corolla 5.25?
No, page 28, it's section 6.1,
Okay.
exponential. Alright, let's try to cruise through here. So the exponential is entire. You have the law of exponents, and exponential of 0 is 1, and the exponential is always a unit because it can't be a zero divisor. It's actually very interesting. See, because exponential to minus z is exponential as the inverse. So the entirety is proved by the fact that the lim sup is 0. Then there's that page equation 84, right?
Yeah.
I'm using, product of two power series is just basically collect the coefficients and like so. So that's that. I mean, once you know that e to the z times e to the w is e to the z plus w, the fact that e to the minus z is e to the z inverse is easy to see, right? Because or if we like, we could denote it 1 over e to the z. Sometimes we do that still, you know.
See, but while it's entire on A, it's not entire on the reals.
What do you mean? Which is not entirely reals?
I'm looking up there in 6.2. Like EX, like the exponential of Z. Because on the reals, isn't it restricted from 0 to infinity?
Well, if we I mean, I think if you just if you restrict this exponential to the reals, it's just the ordinary exponential. It's just, so that's entire. It's fine.
Oh, okay. I thought entire meant you had to like capture the whole domain of the reals. The domain had to be the reals, like so.
Yeah, the domain. Well, it's not just it's that there's a single power series which converges on the whole real line, and that is the formula for the function. That's an entire function on the reals.
Okay.
And if we restrict the a exponential to the real line, it does give us the power series for the real exponential, which then you could say is the real exponential. The question is, now this is going to be somewhat semantic. How do you define the real exponential? Is it defined in terms of a power series? Like, there's about 5 different competing definitions for the real exponential, at least. So,
I didn't know that was a thing.
and then like theorem 6.3, the derivative of the exponential is the exponential. That's just from term by term differentiation, right? You can prove that. Easy. And now before I go on to anything else, I just take a second to say, okay, well, this is lovely, but what is this exponential for different choices of the algebra, right? Like, what is this thing we're talking about? Let's be a little bit less abstract. So, if the algebra is the reals, the exponential is just the plain, it's the exponential, right? But it's, we're at it. So, a equals to r, then, you know, e to the z is e to the x. It's just the usual exponential. Complex numbers. E to the z is e to the x plus iy, right?
Yep.
And that is actually e to the x cosine y plus I e to the x sine y. So that's the so-called complex exponential. There's many beautiful properties. Hyperbolic numbers. And this is one of the things I found early on with Spencer and Min and Belu, and it was like, oh, this is so cool. So if this is e to the x, e to the jy, well, like what happens with e to the jy?
Well, they just add.
That's 1 plus jy plus, I'm going to show you over 2 factorial, jy cubed over 3 factorial, right?
Mm-hmm.
So what happens to the j's?
They go to 1 every
other time, right?
Yeah.
So you get like 1 plus 1 over 2 factorial y squared, right?
Mm-hmm.
Plus 1 over 4 factorial y to the 4th plus j times y plus 1 over 3 factorial y cubed 1 over 5 factorial y to the 5th. See, so all the odd powers of j, there's a j that survives, like, right? And then the even powers, j to the squared, j to the 4th, j to the 6th, j to the 0, those are all just 1. But then, if you know your power series, you can recognize that's cosh, that's sinh. So for hyperbolic, the exponential is e to the x cosh y plus j e to the x sinh y. So isn't that beautiful? Like,
Yeah.
Complex exponential's got cosine and sine. Hyperbolic exponential's got cosh and sinh. Just like that. I thought this was really, really cool when I first found it, because I've seen none of this in any book ever.
Yeah.
And it's pretty simple, actually. And then shortly thereafter, we discovered the Wikipedia article on this stuff, and we're like, oh, this stuff is known to a select group of people, not widely known. Dual numbers. So that's z equals, x plus y epsilon, where epsilon squared is 0, right? So e to the z is e to the x plus y epsilon, and that's e to the x times, you can look at it like this way, right? This is how I usually attack
Yeah,
this.
but the same thing here happens, but you only the odd number powers survive.
Mm-hmm.
So you get y plus 1/3. Yeah.
1 plus y epsilon, right? Plus what, 1/2 y squared epsilon squared plus da da da. But what we can,
All evens.
yeah, but it's worse. This says that e cubed is also e times 0.
Oh, it's 0.
It's right. In fact, so like,
Wait, so you're only left with e to the x?
well, you're only left with these two guys.
Oh, yeah.
So this is 0. So the null number exponential is e to the x plus epsilon y e to the x. Of course, you can always factor e to the x out, right? You can start to see that over a arbitrary algebra, right?
E to the x times their.
If x is the real variable corresponding to the identity in the algebra, there should be an e to the x that factors out of the exponential formula. And then the other things are what comes from whatever else is in the algebra that's not in the identity, paired with the coordinates, which aren't corresponding to the identity.
What does cosine look like in the null numbers? Because I'm thinking it's going to look very much similar. That
Yeah, cosine is
1.
just 1 in the null numbers.
Yeah, and then
Cosine is a constant function in the null
and
numbers.
then sine would be just epsilon, right? Or epsilon.
Sine of z is just, well, it's complicated because the question is like, ooh, I was wrong. It's complicated. So z equal to x plus epsilon y, right? So what's z squared equal to? I said it's 1. I think that was too fast. Let me work it out a second here. X squared, right? Plus 2 epsilon xy. The epsilon squared term is 0, but the epsilon term survives. And like z cubed, what's that?
X cubed.
Okay, we can piggyback our way up, yeah.
2 epsilon xy cubed. 2 epsilon. That'd fail. Then you get an x cubed. So it'd be 2x cubed.
So we get x
4.
cubed.
And then plus 4 exy. Yeah, x cubed y, I think.
Yeah, you've got a yx squared term, right?
Yeah.
And you've got
xy squared. No, we don't.
I guess we get
2 of them.
3. You get 1 for this. You get 1 for this.
Yeah.
And 2 for that. And I think it's always yx squared, isn't it?
Yeah.
So it's 3 x squared y, right? So maybe you can see the pattern at this point. Z to the n is x to the n plus n epsilon x to the n minus 1 y.
Yeah.
That's very weird. So what that means is that cosine of x plus epsilon y is 1. Plus, well, minus rather, excuse me. x squared plus 2 epsilon xy, right? And then plus, it's supposed to have a 2 factorial. Number 4 factorial, x to the 4th plus 4, excuse me, I can't do math, 3 epsilon xy. You know, I don't remember looking at this before. I'm sure, I feel like we must have done it in 2012, but my memory of doing this is completely wiped.
Well, I'm just thinking if you do the same thing with sine, something's going to happen where it...
I do think something neat happens here. So like,
Because if you add sine to it, it should flip, right?
well, what I'm saying is, what happens here, if you collect the x's, what do you got? Like, what's 1 minus x squared over 2 plus x to the 4th over 4 factorial and so forth? Well, that's the ordinary cosine.
Yeah.
So the real part of this is just straight up cosine of x. And then you've got these epsilon terms, right? Then there's always a y, so we can factor out epsilon y. And what are you left with? You got like x, so the 2 over 2 factorial is just 1, so that's like x. I'm gonna put the minus out here. And then, so I get minus and minus, get a plus over here. 3 over 4 is 3 factorial. And I have x to the, that's supposed to be x cubed, I'm a bad. I can't keep x cubed. That is x cubed. So, x, what is this?
Should be that. Sine z.
Yeah, it's not sine z, but
Yeah.
this is sine x, right? So this is kind of funky. Cosine of x minus epsilon y. Sine of x.
Cosine of x plus epsilon y is equal to cosine of x epsilon y sine x. So that means if we do sine,
Now, let me explain to you why this is completely it's probably too strong. Remember, I was just telling you that the usual laws, the usual identities for sine and cosine exponentials still hold? The adding angles formula holds, even for the cosine over the null numbers. So yeah, I can do this direct combat with the power series expansion if I want,
yeah.
or I can engage in this kind of argument. So this is going to be cosine of x cosine of epsilon y minus sine of x sine of epsilon y by the adding angles formula for cosine, which is true over arbitrary algebras.
Who found that out?
This paper proves it. Because it can be derived from the series, the calculus of series over an algebra. I think that was probably known to experts, but I don't think it's been written as plainly as it's written in this paper I'm sharing with you. Okay, so this is 1 plus epsilon, 1 minus epsilon y squared over 2, da da da. So if you look at that, this clearly simplifies to just 1.
Yeah.
And this clearly simplifies to just epsilon y. Because the cube and the fifth and all the other stuff is multiple epsilons.
So cosine minus y sine. Oh, that's a thing, yeah.
Yeah. And so the other thing you're thinking about, the sine of epsilon, x plus epsilon y, we could just do, okay, so that's sine x cosine epsilon y plus cosine x sine of epsilon y. There's the adding angles.
So EY, so you get, right here would be 1, so sine x plus cosine x ey or ey cosine x.
Right. This is very fun,
Mm-hmm.
right? Like, and the sophistication of this stuff is about calculus 2-ish,
Yeah.
right? But you have never seen this anywhere else, right? I mean, it's the Wild West. I mean, and so you can ask other questions like, okay, well, how about the 3 hyperbolic numbers?
Mm-hmm. Should work there too.
Yeah, what's the exponential look like there? Right? So like 3 hyperbolic numbers, remember those?
Mm-hmm.
So e to the x plus jy plus j squared z, so to speak.
Mm-hmm.
So it turns out that, of course, this is, you know, well, anyway, this turns, I mean, you can rewrite this as some function oh, sorry, I'm trying to think of a
Well, z equals that. Oh, why are we writing like e to the z? And then we rewrite e to the z as.
yeah, well, so the critical thing here is that j cubed is 1, right?
Mm-hmm.
So if you take the power series for exponential, right?
Mm-hmm.
You can break that into the sum over j,
But go away only every other third.
3j factorial,
Yeah.
x to the 3j.
Mm-hmm.
J is a bad choice of letter here.
Okay.
Yeah. Fair enough. And then sum k equals 0 to infinity 1 over 3k plus 1. And so that completely partitions the integers into these multiples of 3, multiples of 3 plus 1, multiples of 3 plus 2. That's everything.
Mm-hmm.
So this is just rewriting the exponential, right, as the sum of these 3 functions. And so we call this one Larry. This is Mo, and this is Curly. This is my terminology. Spencer, to my knowledge, refuses to use this terminology. And there was much consternation when I started using that terminology for these. Although I feel like at that point they were wise to me, so they wouldn't acknowledge that they were they were like, they were annoyed, but they weren't going to give me the satisfaction of making their annoyance too manifest. So like I could see it was there, but it was below the surface. But the point is, since e to the x is, you know, Larry of x, Mo of x, plus Curly of x, where these are the functions defined by these power series, each one of these is entire.
Then we know from that other theorem that if you add them. Oh wait, but I thought that was just multiplying.
So like when you extend to
Yeah.
the whole of the 3, I mean you could take this entire function, you could extend these over any algebra you like. It just is most interesting when you do it over the 3 hyperbolics, because then you've got like Larry of z, Mo of z, Curly of z, right?
Mm-hmm.
And more to the point, if you look at e to the
like, how's it go? E to like the jx, where x is the real variable. Well, then you've got Larry of jx, Mo of jx, Curly of jx, right?
And that's where it gets really interesting because, like, Larry of jx is just Larry of x because,
Yeah.
not ln, L of x, because j cubed, j to the sixth, whatever, is 1.
Yeah.
In the contrast, the Mo, if I give Mo of jx, well then when j gets, yeah, I always have a residual j left over it, so it's just j Mo of x. And likewise, Curly of jx simplifies to like j squared Curly of x. So when I look at e to the jx for this exponential, I am left with the rather neat result, although the reason it's neat is not clear to you yet. But what you end up with, of course, is Larry of x plus
J Mo.
j Mo of x
J squared J Curly.
Curly of x. Which means that Larry, Mo, and Curly are the component functions of like e to the jx. The reason this is interesting is you got to think about what this is analogous to, right?
Like just like the it just looks like the straight up equation for.
So you should compare this to Euler's formula. E to the I x is cosine x plus I sine x.
Okay.
So Larry, Mo, and Curly play kind of the same role as cosine and sine do for I. These are the functions which kind of play the same role as sine and cosine, but for j, such that j cubed is 1. All right, let's go back to the paper.
Do my car move fast?
Oh, I can make you coffee.
Yes, I have a little bit of a 5 hour in there.
I was afraid of that. I'm just kidding, you're fine.
There's this thing called margarine, and it's supposed to have caffeine in it, and I did not like it. It becomes like a paste after a while.
Sounds unpleasant.
It is very unpleasant. It's supposed to give you the B vitamins and caffeine like through your gums, so it goes faster, but not very good. It just becomes a paste because there's not enough gum.
I see. Okay, so so this is the wild world of series over in algebra, and so to summarize, while the theory of convergence and divergence, especially the divergence part, is modified in a significant